Hello everyone, welcome. In this video we're going to be introducing differential equations. Let's get started. So the differential equation is just a fancy word for a derivative. You know, dy on dx, I think you've dealt with it before. Dy on dx equals to, let's say an example, 3x plus 5. This can also be called a differential equation. Okay, it also can be something like dy on dx equals to e to power x. Okay, anything that is a derivative is also a differential equation. Just have a different name because we want to solve it a bit differently. Okay, when we don't really talk about solving derivatives. There's not such a thing about as in solve a derivative. We usually ask you to find a specific point using a derivative, or use a specific point to find the derivative, but we don't really solve derivatives. Okay, we don't solve, but we can solve differential equations because we have given them a name now, so that we know that actually when we solve them, we're actually just integrating. So again, we solve differential equations because we just named them that way. We name them differential equations so that basically when mathematicians talk together, they say, oh, I've solved the differential equation. They just mean they've integrated it. Okay, so to solve a differential equation, I'm just gonna shortcut differential equation for DE, is to integrate it. And the reason we call it solving is because most of the time mathematicians really just require the general solution without really knowing the C. You know how when you integrate something you're gonna get a C? In differential equations we don't really care for the C. Okay, we just mostly, at least most of the cases, we're going to be solving differential equation to basically just identify some property about this previous equation that was before the derivative, the primitive. Right? We want to be able to identify what family of functions it belonged to, and just say that it would have been any one of these members of the family, excuse me. So this is just what it means to solve a differential equation. It's just to integrate it, find the general solution, and say that this belonged to a certain family, identify the properties of the original family without really having a specific solution. If you were given initial conditions like an initial point, example, if you're given something like 0, 1, well, now you're able to find the constant, am I right? So that, of course, that depends on the number of constants you have in the equation, but let's say there's only C. Assuming C is the only constant, you're pretty capable of finding a C and thus finding a particular solution to the differential equation. So let's start with a simple equation. And now notice we're not talking here about higher order differential equations. In this video, I'm only talking about first order differential equations. What it means to be a first order differential equation is just to be, a derivative of just a normal derivative, not the higher derivatives like dt y on dx2, the second derivatives, and so on. We're talking here only first derivatives because this is what was going to be useful for us in the chapter for the A level. So let's start with this equation over here. dy on dx equals to 2x minus 3. Again, to solve a differential equation is just to integrate it, so we're going to be trying to integrate both sides. But this does not really work. You can't integrate something without any respect. You have to integrate something with a certain respect such that we are able to, add x or y or whatever you need. So obviously, before integrating, we're going to have to send one of these respects to the other side. And because we have x here, we're going to send this x to the other side by multiplication. So I multiply on either side by dx, which results in the cancelling of it on this side. Now I'm capable of integrating this just fine, and I just put the integration. So the first step of differential equations is to separate our respects. So separate. Step number 2 is to integrate, and that results in y being equal to x squared minus 3x plus c. If given initial conditions like 0, 1, I would call this step to concentrate. Obviously, that doesn't make any sense. I just mean by that to find the constant because many people usually forget to get constants. So I just say, oh, separate, integrate, concentrate, which doesn't make any sense. It's just, there for remembering. Now let's try another example. We're assuming here that there is no particular solution. Okay, what about something like dy on dx equals 1 over x squared y. I understand it's a bit weird, I understand, but we're able to integrate this just fine. Notice I need to separate, integrate, concentrate. Nothing, too difficult. Just go ahead and separate your limits, and also, not limits, to the respect or the dy and the dx, and obviously separate in turn the variables. So let's start with the dy on dx. So dy will equal to 1 over x squared y, taken with respect to x. Now notice here that we have y, and we can't integrate y with respect to x. We have to send this variable to the other side, and thus I multiply each side by y. And so I get y with respect to y equals to 1 over x squared dx. Now I can integrate either side just fine. Separate done. Now I'm integrating. That becomes y squared over 2, which equals to, where is it up with a negative power? So just the integration of x to the power of negative 2 taken with respect to x. I get y squared over 2 equals to x to the power, add 1 to the power, divide by the new power, negative to the power of negative 1, and add a c. As I have mentioned, to solve a differential equation is basically to find the family of solutions, basically, of which, this guy was supposed to be a part of. So this over here is a general solution, that's true. But we want to know the family that it belonged to, and at this point it doesn't really look like it belonged to anything, especially with the weird relationship between y and x, where we have y squared on 2 on one side and then minus x plus c on the other. We are very much used to having y be subject, right? But we don't really need y to be subject most of the time. Sometimes you just need the relation between y and x, whatever that relation may be. It just needs to be a relation between two functions. And two functions doesn't mean a function with some other things going on to it, like this 2 clinging onto the bottom of the y. Y squared is considered a function. Y divided by 2 is just, a process. It's not really a function, unless we have a linear function, but we're not considering this to be a function in this case. So what I want you to do is to make sure there are no coefficients of y, and that there are no parts of the function. Let me show you examples. So first things first, I just don't want something like coefficients, so I'm just going to be multiplying by 2 onto everything, and so this gives me the relation between y and x, right? It doesn't give me y as subject because he didn't really ask me for y to be subject. Most questions he won't ask you to make y subject, okay? But it's important to have a relation between y and x, and so we can't have y squared over 2. You could just move the 2 to the other side. It will be far easier for you to deal with differential equations and with life in general. So just send any coefficient of y to the other side. Send any, something added onto y to the other side, something like this. Y plus 1, all of it squared, is very unacceptable. Okay? So I just want you to know that you would want to most preferably take the square root on either side and then send y1 to the other side by subtraction, because y really doesn't appreciate, not necessarily just y, but I mean just any variable. When we talk to differential equations about relationships, we don't want any translations, we don't want any addition, subtraction, multiplication for dilation, or what's it called, division for, this type of stretch and that kind of, transformation. We don't want this. We just want the function as it is on one side, okay? So that's basically what I want for you to understand, is if he asks you to get y in terms of x, you are obviously to make y subject, meaning you're going to take the square root. But if he just asks for relation between y and x, you don't necessarily need to take the square root. You can keep it this way, as long as y doesn't have any coefficients, as long as y doesn't have any translation with it, as long as x also doesn't have this thing undergoing it. Usually it's going to, but this is not going to be something that you can do anything about, so we're going to keep it that way. I'm going to be showing you other examples, so let's go ahead and try this one. How about the x taken with respect to y squared plus 1 over y. And we have an initial condition this time of 1, 0. Let's do it. So, first things, separate. We're going to say it's equal to y squared plus 1 over y dx. I can cancel the y on this side by multiplying by the reciprocal on either side, because I want the y to be taken with respect to y. So y here cancels with this. I get y over y squared plus 1 times x dy equals dx. Notice that the x has very out of place here, so I'm going to be dividing by x on either side. Cancel, cancel. I get y over y squared plus 1 with respect to y being equal to 1 over x dx. I can integrate either side just fine. I know here I can use the division rule, so I multiply by 2 up and down, and I get 1/2 ln of y squared plus 1, which equals to ln of x plus c. I hit upon the same problem. Before I deal with the problem of the relation of y and x, first things first, let's use the initial condition to find the constant. So 1/2 ln of, I believe it's 0, yes, 0 plus 1, which equals to ln of 1 plus c. Ln 1 is 0 on the calculator, therefore c equals to 0. Next, I'm going to have to deal with the problem here. Y being with something else on it, right? There's a translation to the function, which is obviously not cool when it comes to relationships between y, the function y, and the function x. Not the function y that's translated, i.e. 1 unit upwards, and x. Okay, so what I need to do here is to, first things first, just remove this one. To remove one, I need to remove the ln. To remove the ln, I need to get the power here. So I'm going to continue right here. Cancel the ln's. You get y squared plus 1 to the power of half equals to x. We can square everything, which obviously cancels the half. I'm going to add another page. We're going to say that here y squared plus 1 equals x squared, which means we can leave it right now as this form. As long as y is not linked to 1 by a certain mean, meaning it's a function with 1, we're good. This over here is a relationship between y squared and x squared. If I asked you to get y squared in terms of x squared, I'll say, okay, y squared equals to x squared minus 1. If I asked you to get y in terms of x squared, I'm going to say, okay, I'm going to square root either side, and I'm going to get y equals to the positive or negative of x squared minus 1. So it just depends on what he asks you, and you're going to get used to it when you solve, and it's not going to be that big of a deal, actually, as you solve. I'm just trying to warn you as what's the definition of a relation, what's the definition of a, in terms, okay? Anyways, I'm going to give you one last example. So let's go ahead and do this one. X squared dy on dx equals e to power y with initial conditions of 1, 0. So again, separate. X squared dy equals to e to power y dx, meaning dy divided by e to power y will equal to x squared, 1 over x squared, dx. Integrate either side, so you get the integral of 1 over e to power y taken with respect to y. Integral, I'm going to raise this with a negative power. Same thing for the e to power negative y. Now x to power negative 2, we can add 1 and divide by the new power, which is going to be negative 1. Meaning I'm going to get x to power negative 1 plus c. On this side, I can just divide by the derivative of the power, meaning it's going to be negative e to power negative y, which must equal to negative x to power negative 1 plus c. As I have mentioned, we're going to need to find a constant, so let's go ahead and concentrate. So instead of the y, you're going to put 0, which must equal to negative 1 to power negative 1 plus c, meaning we're going to have c being equal plus minus 1 being equal to minus 1. C is equal to 0, and so we get negative e to power y being equal to negative x to power negative 1 without a c. And because it's a relation, this is a very inappropriate form to keep it. I'm going to need to have at least the power be positive, and I'm going to try to make y subject because it's just more comfortable and more relaxing for both me and you. So let's just go ahead and make y subject. So to do this, first things first, we can, flip everything, because I have negative powers, which just represent the following. I can cancel the negative, and I can now flip, right? So I get e to power y being equal to x. If I get ln on either side, I get y outside the ln, because that's the power coefficient rule, which equals to ln x. Ln e is equal to 1, therefore y equals to ln x. And there you go. Okay, please just try to avoid this problem of in terms and relations. If you can, make y subject. If you can't, it's fine. Just make sure that y is not being translated or being stretched. And that's it. Have a nice day, everyone.